Here we have an example. Let A contained in R be non-empty and bounded above, and let C element of R, where R is a set of real numbers. Define the set C plus A by C plus A is equal to set of all C plus small a, where small a is an element of capital A. Then supremum of C plus A is equal to C plus supremum of A. Now let's see what is given in the example in detail. So you are given that A is a non-empty subset of the set of real numbers which is bounded above. So A is non-empty subset of R which is bounded above. And C is any real number. C element of R means C is any real number. Now we are defining the set C plus A by C plus A is equal to set of all C plus small a, where small a is an element of capital A. Then we have to show that the supremum of this set C plus A is C plus supremum of A. So you have to show that this quantity C plus supremum of A is the supremum of this set. Just to remind you of the definition of supremum, real number S is called the supremum of the set A if S is greater than or equal to the every element of the set. That means S should be an upper bound. Second thing is that if B is any other upper bound of the set A, then S should be less than or equal to B. So if S satisfies these two conditions, that means the first one is that S should be an upper bound, and second one is that if B is any other upper bound of the set A, then S should be less than or equal to B. So if these two conditions are satisfied, then we call S as the supremum of a set A. This is the definition of supremum. Now, when we come back to this example, you are given that A is a non-empty subset of R which is bounded above, and C is any real number, and the set C plus A is defined as C plus A is equal to set of all C plus A element of A. You have to show that supremum of C plus A is C plus supremum of A. So you have to show that C plus supremum of A is the supremum of this set C plus A. To prove that this is a supremum, it should satisfy two conditions. First is that you have to show that C plus supremum A is an upper bound of the set. Secondly, if B is any other upper bound of this set, then you have to show that C plus supremum of A is less than or equal to B. So these are the two steps which we will be doing. So firstly, we will take this supremum of A as S for convenience. So let S is equal to supremum of A. Then by the definition of supremum, supremum means the least upper bound. That means it is an upper bound. So S is an upper bound of the set A. So you have A is less than or equal to S for every A element of capital A. Now we add a C to both sides. So we will get C plus A is less than or equal to C plus S for all A element of A. C plus A is an element of the set C plus A. And we got that every element of C plus A is less than or equal to C plus S. So this means that C plus S is an upper bound for the set C plus A. Let B be any other upper bound for the set C plus A. That means C plus A is less than or equal to B for every A in the set capital A. as B is an upper bound. From here, you will get, you move C to the other side, you will get A is less than or equal to B minus C for all A element of A. This means that B minus C is an upper bound for the set capital A. Now, S, as S is equal to supremum A, we know that S is the least upper bound. And here we have B minus C is an upper bound. And since S is the least upper bound, we will have S is less than or equal to B minus C. Now, if you move this minus C here, you will get C plus S is less than or equal to B. Now, we started by saying that B is any other upper bound for C plus A. And we have shown that C plus S is less than or equal to B. So this means that C plus S is the supremum of the set C plus A. So we can say that supremum of C plus A is C plus S. And replacing S by, remember initially we took S as supremum of A. So replacing the value of S, we will get this is equal to C plus supremum A. So we got that supremum of C plus A equal to C plus supremum A, which completes the proof of this example. Here you have a lemma. Assume S element of R is an upper bound for a set A subset of R. Here R is the set of real numbers. Now you are given that S element of R is an upper bound for a set A subset of R. That means the real number S is an upper bound for a set A. Then S equal to supremum of A if and only if for every choice of epsilon greater than 0, there exists an element A element of capital A satisfying S minus epsilon less than A. Now you can see that there is a if and only if condition used in the lemma. So the proof of this lemma will have two parts. One, the forward direction, and another one, the backward direction. Now, to prove the lemma in the forward direction, we will assume that S is equal to supremum of A. And we have to show that for every epsilon greater than 0, there exists an element A in capital A satisfying S minus epsilon less than A. So first we assume that S is equal to supremum A. Now we know that for epsilon greater than 0, S minus epsilon will be less than S. Now S is supremum A, which means the least upper bound of A, which means the smallest upper bound of A. That means any number less than S will not be an upper bound of A. As S minus epsilon is less than S, we can say that S minus epsilon is not an upper bound for the set A. Now S minus epsilon is not an upper bound for the set A means there exists an element A in capital A such that A is greater than S minus epsilon, as S minus epsilon is not an upper bound. This means that there exists an element A in capital A such that S minus epsilon is less than A. Now what we have done here is that we have started by assuming S is equal to supremum A, and we have shown that for every epsilon greater than 0, there exists A element of capital A such that S minus epsilon less than A. And this completes the proof in the forward direction. Now to prove the backward direction, we will assume that S is an upper bound for the set A, and for every epsilon greater than 0, there exists an element A, element of capital A, satisfying S minus epsilon less than A. Now, as there exists an element A in capital A satisfying S minus epsilon less than A, you can say that S minus epsilon is not an upper bound for the set capital A. Now, by assumption we know that S is an upper bound for the set A, and here we got that S minus epsilon is not an upper bound for A for any epsilon greater than 0. Now this means that S is the smallest upper bound of A or the least upper bound of A. Least upper bound of A means supremum A. So we get S is equal to supremum A, and this completes the proof in the backward direction. Here we have another lemma. Assume I element of R is a lower bound for the set A contained in R. This means the real number I is a lower bound for the set A. Then I is equal to infimum A if and only if for every epsilon greater than 0 there exists an element A, element of capital A, satisfying I plus epsilon greater than A. Now, as there is an if and only if condition used in this lemma, the proof of this lemma will have two parts. One is the forward proof in the forward direction, another one in the backward direction. So, for the forward direction, we will assume that I is equal to infimum A, and we shall prove that for every choice of epsilon greater than 0, there exists an element A in capital A satisfying I plus epsilon greater than A. So we assume that I is equal to infimum of A. Now we know that for every epsilon greater than 0, I plus epsilon is greater than I. Here I is the infimum of the set A. Infimum means the greatest lower bound. That means any number greater than I will not be a lower bound of the set A. Since I plus epsilon is greater than I, this means that I plus epsilon is not a lower bound of the set A. As I plus epsilon is not a lower bound for the set A, there exists an element A in capital A which is less than I plus epsilon. This means there exists an element A in capital A such that I plus epsilon is greater than small a. So we have started by assuming that I is equal to infimum of A, and we have shown that for every epsilon greater than 0, there exists A in capital A such that I plus epsilon is greater than A. This completes the proof in the forward direction. Now, to prove the lemma in the backward direction, we shall assume that I is a lower bound for the set A. And also, for every epsilon greater than 0, there exists an element A, element of capital A, satisfying I plus epsilon greater than A. Now, since there exists an element A in capital A satisfying I plus epsilon greater than A, implies that I plus epsilon is not a lower bound of the set A for any epsilon greater than 0. Now, we assume that I is a lower bound of the set A. Now we got that I plus epsilon is not a lower bound of the set A for any epsilon greater than 0. This means that I is the largest lower bound or the greatest lower bound of A. Greatest lower bound of A means infimum of A. So we get I is equal to infimum of A, which completes the proof in the backward direction. Now here we have something called the axiom of completeness, which states that every non-empty set of real numbers that is bounded above has a least upper bound. This means that if A is any non-empty subset of R which is bounded above, then A has a least upper bound. That means A has a supremum. So this property is known as the axiom of completeness, and this is a very important property in real analysis. Here we have a question. Part A of the question is, let A be non-empty and bounded below, and define B equal to set of all B element of R such that B is a lower bound for A. Now the set B consists of all the real numbers which are lower bounds of the set A. Show that supremum B equal to infimum A. Now the B part of the question, use A to explain why there is no need to assert that greatest lower bounds exist as a part of axiom of completeness. Now hope you remember the axiom of completeness says that a non-empty set of real numbers, if that is bounded above, then it has a least upper bound. So the axiom of completeness does not say anything about lower bounds of or the greatest lower bound. So here we have to use the proof used in A to explain why that it is not necessary to specify about the greatest lower bounds in axiom of completeness. To prove the A part, we are given that A is non-empty and bounded below. Now since A is bounded below, A has a lower bound, and this lower bound will be an element of B by the definition of B. So we can say that B is non-empty. Now for all A element of A and B element of B, we have B is less than or equal to A. This is by the definition of B because B consists of all the lower bounds of A. If you look at this carefully, for every B element of B, B is less than or equal to A. This means that B is bounded above. Now, earlier we got that B is non-empty. Now we got that B is bounded above. Then, by the axiom of completeness, B has a least upper bound or a supremum. Then we call that supremum as alpha. That means alpha is the supremum of B. From equation 1, we have every B in B is less than or equal to every A in A. This means that every A in A is an upper bound for the set B. So every element of A is an upper bound for B. And alpha is the least upper bound for B. So therefore we get alpha is less than or equal to A for every A in A. Because every A in A is an upper bound and alpha is a least upper bound for the set B. Now this alpha less than or equal to A for every A element of A implies that alpha is a lower bound of the set A. Our motive is to prove that we already have alpha is equal to supremum B. We have to show that supremum B is equal to infimum A. For that, we already have alpha as supremum B, then we will show that alpha is equal to infimum A. Now we already have that alpha is a lower bound of A. To show that alpha is equal to infimum of A, let L be any other lower bound of A. Since L is a lower bound of A, we get L is an element of B by the definition of B, because B consists of all the lower bounds of A. So since L is the lower bound of A, L will be an element of B. Now since alpha is the supremum of B and L is an element of B, we will get L is less than or equal to alpha. Now what we got is that we had alpha as a lower bound of A, and if L is any other lower bound of A, then we got that alpha L is less than or equal to alpha. Now this means that alpha is the greatest lower bound of A. Greatest lower bound of A means the infimum of A, and so we get alpha is equal to infimum A. Therefore from here, from this and this, we get supremum of B is equal to alpha, and which is equal to infimum of A. This completes the proof of A. Here what we have seen is that if A is non-empty and bounded below, then infimum of A is equal to supremum of some other set B. So this is the reason why in the axiom of completeness, it is not specified that if the set A is bounded below, then it has a greatest lower bound. The reason is that if it is bounded below, then it can be, the infimum of A can be expressed as the supremum of some other set B. So this gives a clarity to part B. The next question, assume that A and B are non-empty, bounded above, and satisfies B contained in A, B subset of A. Show supremum B less than or equal to supremum A. So here you are given that A and B are non-empty, bounded above, and B is contained in A. You have to show that supremum of B is less than or equal to supremum of A. Now, we are given that B is contained in A. B is a subset of A. So from here we can say that every element of B will be less than or equal to the supremum of A. Every B in B will be less than or equal to supremum of A. Now this means that supremum of A is an upper bound for the set B. Since supremum of A is an upper bound for the set B, the least upper bound for B, which is supremum B, will be less than or equal to this upper bound. So we get supremum of B is less than or equal to supremum of A.